Christoph Stephan, Almost-Commutative model building in the LHC-Era.
Yeah. First of all, thank you very much to the organizers for inviting me, for organizing this really nice, well, succession of workshops, summer schools here at the Hausdorff Institute. And what I want to talk about is almost-commutative model building in the LHC-Era. And I think I will create a little bit of redundancy with Fidelis talk, but since the audience is, I gather, mainly built from mathematicians, it's perhaps not too bad to have a little bit redundancy on the particle physics side, because it is usually not the thing mathematicians are finally concerned with. So, but of course, I will also build, as everybody give a lot of redundancy on the non-commutative side, so repeating that and so on the whole game. So I want first to talk about basic ideas, then how particle on the particle physics side and physics side, and on the non-commutative side, then tell you how to put particle physics into geometry, talk about some details of the physics, which are, I mean, they come from time to time in talks, but I guess not generally known. And then tell you how to go perhaps beyond the standard model. We already had, in a certain sense, in Fidelis talk, beyond the standard model talk. And there will come probably different beyond the standard model talks when Latham and Chain give their talks. And so there's a bit of physics now coming ahead. And the reason why we want to go beyond the standard model in the first place, I should first also explain. So, some basic ideas, some really basic particle physics. So, known particles of the standard model. The standard model pops up several times, so I just showed you perhaps what the standard model looks like and what we think is the standard model. So, very, very easy. What we have is basically three types of particles. We have on the one hand the fermions, this is this bit, I'll go into some details in a second. We have the bosons, these are these bits here, the Lund boson, and so on. And we have the Higgs boson. So, thinking from a mathematical point of view, the bosons are closely related to, from one point of view, from the differential geometric point of view, to connections on principal fiber bundles. So think, if you see boson, think connection, principal fiber bundle. The fermions are associated vector bundles to this principal fiber bundle, which is usually enormous and complicated and has many details. And so they are even a bit more, they are special vector bundles, they are twisted spinor bundles. And it's the details of how the structure group of the fiber bundle is represented on this associated vector bundle that tells you how the interactions work, so which, via the covariant derivative, which fermion interacts with another fermion. Problem is to get mass into the game, because what we want to maintain is a certain invariance of the theory. The theory should be invariance under a certain automorphism group, or subgroup of the automorphism group of the principal fiber bundle, which is called the gauge group, which basically just preserves base points. And we want invariance of the whole thing. This is just a physical principle we put in, or one could also say what we just want is that everything is nicely covariant. But then we basically forbid mass terms for for our fermions. We know they are massive, so we have to somehow implement this. And what you somehow smuggle in is an intertwiner between different representations. And this intertwiner is the Higgs boson, which can also be represented as a field. So this is like the differential geometric setup. And the Higgs boson, as Alain pointed out, is not really, has been found, or let's say, we have found processes among these particles here, and particle accelerators, which can be explained with certain intertwiners and couplings in the game. So this is more of a process somehow. It is a delicate point, and it's deeply. Then this is for the classical setting, and you have to go to quantum field theory, and things become really, really complicated, and I don't want to go into this. Strange thing is these, what we have here, a little bit of the details. We have here quarks, and the interesting ones are in the end just the up quark and the down quark. That these make the nuclei of atoms. So 3 of these 2 guys, so in pairs, or up, down, down, up, and so on, make neutrons and protons. They form the nuclei of the atom. The electron goes around in a quantum mechanical way, and this makes the atoms. And from this you get molecules and so on. And then you have the neutrinos, which makes up for the right representation in a way. Strange thing is what we need for everyday life is this column here. The rest is somehow, in a certain way, seems to be redundant, and as Fedele said, the first thing beyond the first column here was basically the muon, which was discovered, and Harvey famously quoted, "Who ordered that?" So somehow. And why there are 3 copies of these? One of this is called a generation. This is completely open. And here the gauge bosons or connections, they basically tell us for the interaction of these. One tries to deduce what is the structure group of the principal fiber bundle. And this is all a very delicate thing. People have been trying around for tens of years to find the right geometrical setup to get this. And one particularly nice thing of non-commutative geometry is that this here seems to be quite a generic, simple model in non-commutative geometry, whereas it's very non-generic, complicated model in the differential geometric approach. So this is somehow perhaps one of the greatest successes of non-commutative geometry.
So the order you have put is gauge bosons on the right column.
It's completely arbitrary. Not completely. This is belongs to an SU3 gauge group or structure group. This is U1, and these 2 belong to SU2. It's basically arbitrary. It's just how Wikipedia. This is from Wikipedia. So, also, didn't put this picture. I cannot make pictures like that. So this is what we think we know and understand fairly well. But to put everything in perspective, if we look at cosmological data and believe in these models, believe in also adding general relativity into the game, and then measure how galaxy moves, how the echo of the Big Bang looks like, so this 3 Kelvin background radiation, and see how galaxies are distributed at the moment, what we see from this echo, how the mass was distributed just after the Big Bang. So this is 380,000 years data, after Big Bang. And if we look how galaxies today move, so how they rotate and so on, we infer from that there's quite a lot of mass which gravitates is absent. So one can say, one can deduce from the whole setup how these should build up mass in galaxies and so on, and one can then see what we experimentally, no, not experimentally, what we observe under these assumptions of these theoretical assumptions, and then we see if we put everything together, the bit is missing, and this bit is a lot. Basically, it's everything. So atoms and everything which is made out of this, or basically this column here, make up 4.9% of the whole energy content of the universe. Then there's matter, so something that should behave like particles, missing, which makes up 26%, 27%, and then there's dark energy. I'm personally not very concerned about dark energy because you can always put into the game, I mean, even here with the general relativity, which is the geometrical theory, you can put in the cosmological concept, which is a perfectly valid geometrical thing. Okay, it doesn't fit into particle physics really well, so there are the usual discrepancies, but this can account for this bit here easily. So I'm not really worried about dark energy. But of course, this discrepancy here is already quite bad. If we look at it, just taking it out, then we see that dark matter is or what's missing is 63% at least, and then the rest is made up from stuff we know. So, yeah.
The picture below doesn't take into account dark energy. Because
No. Here, just take out this and
okay.
800% out.
So this is also Wikipedia.
This is also Wikipedia. I mean, these are the ones which are on the web. So the problem is really, even if we forget about dark energy, it always seems to be 95%. We don't know about 95%, but actually we don't know about roughly 63 to 65% of the mass which is around. And this also doesn't show. This is not only inferred from Big Bang and analysis of Big Bang, but also inferred from rotation curves of galaxies and measure. One can weigh galaxies by looking how light is bent, so one can see pictures from galaxies behind galaxies and see Einstein rings, Einstein crosses, and so on, and see that there is more mass in the foreground galaxy than there can be seen from stars, dust, and so on, what one can measure directly. So there is a lot of mass simply missing, and it cannot be explained easily, or as far as I know, it cannot be explained with the standard model of particles we have. So this may certainly be a reason to go beyond the standard model. So there's no, it has not been detected directly. There have been claims that people think they have seen particles, but up to now, then there comes a data experiment that says no. So there's no direct experimental evidence for these bits, so that somebody has actually seen a particle. There's only an indirect experimental evidence that we see gravitational effects of this. So that's the reason why we call it dark. Because obviously it doesn't end that. Dark is nowadays kind of a fast word for everything, which I understand. It's just a dark.
So it's not possible that gravitation works differently in
Who knows? Gravitation could work on more. I mean, we know gravitation experimentally very well from, I don't know, a couple of millimeters up to a bit more than the solar system, which is a couple of light hours. The galaxy is 100,000 light years, and the universe is 13.7 billion light years, so there's quite a lot of space for change. Who knows? But I mean, on the other hand, general relativity works in other ways very, very well, even on these large scales. So it's nobody knows. So dark. Okay, so that's why I think at least it's worth looking how to go beyond. And since non-commutative geometry explains this bit here very well, perhaps it gives us also clues how this might work. But of course, we are in desperate need of better experimental evidence. Here we're just poking in the dark. Okay, now the stuff everybody here knows probably already quite a lot. This is some transparencies I stole from Barrett. Just to give an analogy, what we want to do is almost commutative geometry. You know the general story. We replace our compact Riemannian manifold. We don't know how to do Lorentzian, so we do it compact Riemannian with a certain function algebra over the manifold. Invoke the Gelfand-Naimark theorem, or we introduce some representation we had yesterday with Planning on a certain Hilbert space and some first order operator, and then we can reconstruct from this whole thing a Connes reconstruction theorem manifold. And what we want to do is to get some non-commutativity into the game, and then we can think about it as the Luther-Klein space, where we take a cross product with some other compact like S1 or some other compact little manifold, and we replace this by finite space. So we go from differential geometry to spectral triple. So what we actually do is we replace our finite space by some or small compact extra manifold, Luther-Klein manifold by some finite space, which is basically matrix algebra, some matrix algebra over some field. And what we then do get is a spectral triple, which is our non-commutative, or in this case, because the commutative bit is very prominent, so almost commutative manifold, so tensor with some finite space, because you have to construct everything in more detail. I'll come to that a little bit later. We have some internal and external symmetries, which are basically the automorphisms of the algebra. One can see all, I mean, one can also take unitaries of this finite algebra, which is, if we choose this algebra correctly, of course, diffeomorphism, which we know like from general relativity, and if we choose the correct algebra, we get the U1 times SU2 times SU3, which is the structure group or gauge group of the standard. And here we get the Dirac operator. For the Dirac operator, we write down the spectral action and get again into details later. And if we do this seeded event like trace expansion, then we get Einstein-Hilbert action, huge cosmological constant, but this is a general problem of these Riemannian theories, or perhaps even in general problem of these kind of theories. And we get this, the interesting of the standard model action, or the bosonic part of the standard model action. So in this setting, we get quite a lot of stuff for free, especially the Higgs boson is the correct Baltic Higgs potential. So we have this symmetry breaking mechanism behind all that, which makes the whole thing work. This is used to be you normally have to put it in by hand, and here in this setting you get it almost for free. And the important bit is basically the Dirac operator, which contains here the gauge connection. So this is the connection. This only has slashes. The connection or the connection covariant derivative with respect to the
the spin connection.
No. The spin connection in my case is here in the delta slash.
Okay.
Here, this is the induced connection from the principal fiber bundle on the twisted spinner bundle, and you get this extra endomorphism field phi, which encodes all the Higgs and Yukawa couplings and particle masses. So what you get in the Dirac operator, you get Higgs and gauge bosons. You get the fermionic mass matrix, particle dynamics in a way, and if you take Connes' length distance formula, you get a metric on the manifold and an internal metric of the whole thing. And what I will be mainly interested in is the particle physics content. And so Higgs or Higgs or more scalar field gauge bosons and fermionic mass matrix. So this is what I'm basically concerned with. And Thijs Vandenbroek has made a very nice picture how to think about these non-commutative or almost commutative manifolds. If you just take part of it, so take this as the electroweak sector of the finite internal space, then we can somehow think this is space-time, which then splits at a certain energy into two sheets, where the Higgs is really giving you, in a way, the distance between the two sheets. One sheet is the complex numbers, and one sheet is the 2x2 matrices. Yeah.
I made the picture.
You made the picture. Tijs made it. You made the logo. Okay, then forget about Tijs. Okay, so let's come a little bit more specific and just tell you what kind of which set of axioms I will basically use, or which is all represented. So even real spectrum triple. This has been here loads and loads of times. So real associative 3C star algebra, which will be function algebra on the space, or tensorize matrix algebra. Simply chosen Hilbert space on which the algebra space will be represented. Self-adjoint first order operator, anti-unitary operator to make the whole thing real, and particle physics, as we did already explain, that can be identified with charge conjugation, and a unitary operator, mathematics, we would say just volume element, we say this is for chirality, so which tells you what's left, what's right, yeah. And then of course we take a set of axioms, so classical dimension, regularity, finiteness, first order, reality, orientability, and usually also Poincare duality. And everything I say here is classical in the sense that all of these axioms should be satisfied. right? So I want to have regularity, so zeros order, and I want to have first order, I want to have everything. So since the standard model fulfills this, and on deviations going from way first order or from zero order that the commutator has done. I'm lying here because I'm not really caring, or I'm keeping the orientability a bit under the rug because there's one particle which always fits into the soup when it comes to orientability, which is the right-handed neutrino. So, and since we need right-handed neutrinos, probably the game perhaps orientability is an axiom one should sacrifice, but it is also an axiom, already an axiom one should sacrifice in the normal standard model without going beyond. So I'm not quite sure what to make out of this that the right-handed neutrino doesn't respect orientability. So I'm still after years and years of thinking about it, so a bit confused what status this orientability axiom has for right-handed neutrino. Yep. Just violates in the internal section, not for the infinity bit, but in this internal. I don't know. So what I want to have it in the game at the moment because everything builds on this classification concept we built in Marseille years ago, and there concrete relativity was just a good discriminator to pick out interesting models. So take it on this reading, and it should be. It is in general for the standard model. It's fulfilled. It's fulfilled for the manifold part. So why not just keep it for the moment? It works fine. So and I like form basically. Just put it in extra axiom. My choice. Okay, let's have a look at finite spectral groups. Because choice of finite spectral group basically tells you what kind of particle content in the game is in the game, and what kind of Ruck operator you are allowed to use, and how the whole particle physics works. So, as I said, finite spectral, the finite algebra is basically the sum of matrix algebras. As a gauge group or structure group, this is transparently used for physics, so physicists usually use structure group and gauge group interchangeably.
So is A a complex algebra?
At this point, it's a real algebra because I also want to put in quaternions, but
So then later you complexify this?
No. I mean, you don't need to complexify.
But in the definition of a spectral tuple, you said complex algebra.
Complex? No.
Real.
Real three-star algebra.
I think basically you take the thing you need for the reconstruction theorem and take it as a real algebra and then just tensorize with matrix algebra. I don't want to get into these details here. So the structure group is basically the automorphism group of your inner algebra, and the interesting bit is, of course, that if you look at the automorphisms of, for example, complex n by n matrices, what you get is the unitaries or non-commutative unitaries of the algebra. And then, of course, if you trace this algebra intelligently, what you get out is an interesting structure group, which may then be compatible with particle physics. As the internal Hilbert space, you basically choose then, or of course has to be chosen in accordance with the axioms, the c to the n. So just a huge c to the n, where n is just the total number of particles in the game, where we count left, right-handed particles, antiparticles, and particles separately. So it's this huge 96-dimensional or Hilbert space called standard model, or even bigger And the Dirac operator is just fermionic mass matrix. In the end, it encodes the U-cover couplings and possible quantum masses. So the basic point is, which makes it interesting, the whole setup interesting for particle physics, is that the axioms put strong restrictions on the choice of this mass matrix and also on the Hilbert space. What I will be playing with around is here the number of summons in the matrix algebra. So usually we put 3, 3 or 4, but you can go bigger. And I'll be playing in a really simple and bit oversimplified way. And then to build this almost commutative geometry, that is basically just take the tensor product of your manifold bit of the geometry with this finite algebra, and you get a Dirac operator, and then the automorphisms are basically sort of the automorphisms you would like to have. It has to play around with this. So the mathematical axioms give us strong restrictions on particle content. So in contrast to the differential geometric setup, we have, because we have these strong axioms, we have really rather restricted class models here. Of course, we can still build infinitely many models, but it's more restricted, and it seems to be interesting. That's basically the only reason why we can do it. The symmetries of the finite space determine the structure group of our principal bundle or the gauge group. The representation of the matrix algebra tell us what kind of representation of a structure group of gauge group we have. And this is, of course, much more restrictive than the approach from principal fiber bundles, because groups just allow for more representations than algebras, simply because you have to always keep linearity with the game. And so we're basically stuck with fundamental and geometrical representations. And the Dirac operator tells us what are the allowed mass terms and what are the allowed Higgs fields. I put another S here, so there can be more than one field. And there will be more than one field. So let's have a look at the physics. How do we get physics out of it? We need an action principle. As Danilo already said, we usually take the spectral action to do that. First of all, we have the Dirac operator, which is then fluctuated, but I will be telling about this, I think, today. Yes. Yeah, so I won't go into this. And what we get out if we fluctuate, there are several ways of doing this, basically. But what we always get out is something that looks like a generalized, twisted Dirac operator with an anamorphism field in the sense of, I don't know, Quillen or Berlin-Gessler, something of this kind of form. So we have here the normal Dirac operator on the 4 spinners on our space-time. We take the 4-dimensional compact manifold, spin manifold for that. We have here the bit from twisting, so which contains the covariant derivative with respect to the principal fiber bundle. And we have here an anamorphism where all the extra new nice scalar fields, where Higgs field is in, perhaps other scalar fields and the U-cover coupling, so it's all encoded in this anamorphism. And then we plug everything into the spectral action. Spectral action has a fermionic part, which is basically an inner product. One has to be very careful because there's fermion doubling and all this involved, so one has to take. There's a projection involved in this inner product, so there's some subtleties, but I don't want to go into these subtleties here at the moment. So this then includes the U-cover coupling, fermion gauge boson interactions, and all that. And then you write down the real spectral action in a way, which is a counting function or a smooth counting function of the number of eigenvalues of the Dirac operator in up to a cutoff or in an interval from, let's say, minus lambda to plus lambda. And then I'll tell you in a second how to extract from this an interesting physical action with the heat trace. We get this Einstein-Hilbert action, and especially the full bosonic action. But also, this is should be interpreted as an effective action, which is valid at this cutoff scale lambda here. This is, of course, slightly mathematically slightly dodgy point, but if we take this for granted and forget about the problems or the difficulties there, then we also get, since this is an effective action valid at this point, we get relations among different physical coupling parameters, which we understand as constraints valid at this cutoff scale, and these give us, as Pedro said, boundary values at the cutoff scale for these parameters, which then have to be run down using renormalization techniques. Or in the end, that's where the quantum field theory is brought into the game to get low energy values. Of course, this is another input which comes not from geometry, the renormalization group equations. And so these constraints basically give us less free parameters than the classical standard model and the classical theory, which makes the theory, if one believes in renormalization group equations and so on, more predictive. So that's the paradigm of the game we are playing. Okay, how to get the physical action or something we recognize from this number of eigenvalues? Well, basically, you perform a Laplace transform and use the heat trace expansion for e to the power, trace of e to the power d squared over lambda squared. Since this is a Dirac type operator, we get the Laplace type operator. We can play the whole heat game level. We can take the heat trace, and in the limit lambda to infinity, of course, you get here heat trace expansion. But we forget about, as I said, we forget about some subtleties. We just take lambda to be finite, but very, very big, and just take the heat trace expansion, the CD expansion, and look at the coefficients and the CD coefficients here. And what we're particularly interested in is the lambda squared and the lambda zero terms. This is where the standard model and gravitational action is hidden. Of course, again, this is Euclidean or Riemannian, and we should go somehow to the Lorentzian, and then we just say, who cares? We just big rotate, and then I get a really, really bad feeling in my stomach. If somebody says big rotation in the same line as we have a gravitational thing going on here, so this is. But again, if we forget about these subtleties, we get an action which looks exactly like the action we want to have in the Lorentzian case. Get it and
so this lambda squared is just 1 over 3 of the or
yeah, exactly. I mean, here you can kind of write t instead of lambda squared, and then let t go to 0 instead of lambda to infinity. Same game. Okay, and if we take this twisted Dirac operator of this, I just called the Connes type Dirac operator, the fluctuating Dirac operator, plug it in, then you get the details. Dedele just lost showed and went on. So in this A2 term, this CD coefficient here, you get scalar curvature. So we interpret this as the Einstein-Hilbert action. We get a trace of the endomorphism field squared with a minus sign in front, and in the A4 term we find the trace of the endomorphism field to the power 4 with a plus sign in front. And if you take these two, what you get is a Mexican hat like W-shaped potential. This is what triggers the whole symmetry breaking mechanism. And
it's different orders in lambda?
Yes. But this is a mass term, so we need a negative mass term anyway. So
I thought they get also a higher derivative gravity coupling.
oh yes, there's one. There's I didn't. There's a bi-term, yes, bi-curvature square. We also get a topological term here, which is the Euler characteristic. We get derivatives of the endomorphism field, which we interpret as dynamical terms. We get squared of the curvatures of the connections, which we interpret as Yang-Mills terms. And we get a conformal coupling between the scalar curvature and the trace of the square of the endomorphism. But the red ones are the ones which are then important for the standard model, and we gracefully forget about the higher curvatures.
Yeah, the flux situation.
I mean, yeah, I mean, any Einstein, okay, this is vacuum, at least any vacuum Einstein solution would also be a solution of, would also be a critical point of this of this functional here. But of course we're not in a vacuum. So yeah.
I mean,
This term, on the other hand, is quite important for. I mean, this is the conformal coupling for field theories on curved space. It's quite important. Yeah.
well, I'm just going to say, I think that the Weyl square term is, you expect it to be there in the quantum affected correct action to gravity, and it's the experimental constraints on its coupling are much not strong enough to rule out its presence there. So it's not in conflict with Einstein gravity.
Yeah, but of course it makes the whole field much more complicated because you have fourth order derivatives in the game, and if you look at the equations of motions, you get this horrible Bach tensor.
How gravity works at large distances with this stuff?
I have no idea. I don't know. Okay, now let's look how we get the standard model out of this. We basically plug in this kind of algebra here, so C plus quaternions plus 3 by 3 matrices. We can also have another complex numbers. What we get as automorphisms is SU2 times U3. There's another U1 hidden in the U3 here. Hilbert space, for the moment we just pick the standard model Hilbert space. We just pick the fermionic mass matrix we know from experiment. Then fluctuations will give us one Higgs field by inner equations, and we can also include in the drug operator Majorana masses, so everything we need for the seesaw mechanism, all the technical details of particle physics. And this is basically the model of Connes, Chamsedy, Marconi, and Majorana masses of Barrett.
What is this plus C in the first line? Plus C?
Oh, this is it depends how you define the gauge group. If you go with the unitaries, then this is too much. If you go with the automorphisms, then the C's don't contribute because they just drop out. And if you want to go to KO dimension 6 according to the normal standard model, then you need an even number of sums with the matrix algebra, so you can add a C without doing anything to the gauge group in a way. This is just how technically how to put this all together. So this is a question of which kind of detailed construction you do.
So that this U1 comes
From the
different real representation of the space, and which is not complex.
Yeah, but it comes basically, you can do it with sample extension. That's the approach of Sugar and Lazzarini, and then you can just get it out of the U3 as a determinant, and then you have one U1. And you can then represent the U3 as SU3 cross U1 on the space with the sample extension. This is a question how you construct this whole thing. So
CP value can be repeated just as a like sense.
Exactly. So what you get then, because basically the quality coupling of the Higgs comes here. You have the dynamical term here, and you have here some of all the Yang-Mills terms. So everything comes from the same Seeley bit coefficients. So all the prefactors at the cutoff are linked to each other, and this gives you then these famous constraints or boundary conditions. And what we find, if G1, G2, G3 are the gauge couplings of your group, that they are interrelated like this. So this is the number of standard model families. As I said in the beginning, it's 3, but I just left it open for the moment. And you get this relation among the gauge couplings. This is here comes from the square of the Dirac operator, which is basically trace of U-cover matrix square, trace of the U-cover matrix, or inner Dirac operator with fourth power. And this is how the quartic coupling, the lambda, is so coupling which is in front of this term here, comes into the game and you get this kind of constraint. The question is now, if we plug in the numbers we know, can we fulfill this constraint? So is the standard model a good model in this sense in non-commutative geometry? And we make a few extra assumptions. Oh, and there is a warning, perhaps, issued. We have believed for quite a long while that if we work with a sample extension approach, that we can get rid of this constraint because we know this one comes. We will see it's not fulfilled. But this is actually not true. There is we get an extra free parameter or free factor from the sample extension, and we lose it immediately because we have to normalize everything. And we know at least, we can measure at least this number at low energies, and this already kills us all the freedom. So we actually have to fulfill this. And there was some, it always was in the literature that we can get rid of this constraint here, but it's unfortunately not true. So we have some extra input now. So we put in what's called the big desert, so that we have the standard model, only the standard model, and that's everything up to the cutoff energy, which is of course quite an extrapolation, because we measure up to 10 to the 3 GeV if we are lucky now with the LHC, and the cutoff scale turns out to be 10 to 17 GeV, so 14 orders of magnitude. Extrapolation is quite daring. What we put in is the measured numbers for these couplings. We can measure these at the measured experiments. We put in renormalization group equations. So this is basically the tool. We will calculate the value of these things here in a call we can calculate the value of these at high energies, and then we have to run them down and compare them to these numbers here, and to get to low energies we put in renormalization equations. It's just the tool one uses. So it is here an extra input. We put in the top quark mass, which basically gives us a handling on this term here, which is basically dominated by top quark. And if we put this in and believe in it, then the output is that G2 equals G3. If we take this as part of the constraints here, is fulfilled at 10 to the 17 GeV. We can also get out an upper bound on the top quark mass. It should be lower than 190 GeV, which is good, because it is. It was done by Hausdorff and Trimester, and we get out that there shouldn't be a fourth generation, because that would violate experimental data. Also good, because we haven't seen one at the LHC. But anyway, this whole thing is excluded by Tevatron. As we said, we get out the Higgs mass, or the coupling of the quartic coupling is such that the Higgs mass should be around 170 GeV, and it isn't. It's 125, and this constraint between G1 and G2 or G3 is not fulfilled. So, and there's another slight problem. There's another slight problem with these values here. If we have a Higgs mass of 125 GeV and believe in this renormalization group equation game, then you find also that if you run from the Higgs coupling up from the measured value, that you drop into the negative values of lambda. This hints into vacuum instability, and this might be also a problem. So this might be, the whole thing can be seen as another hint, apart from the whole dark matter business, that there's more than the standard model to it. And indeed, if we include these extra fields, which Fidel already spoke about, you can, for example, keep this coupling parameter positive. So then there's quite intricate interactions between everything, and the renormalization group equations look differently, so this all lifts everything a bit into the positive and things like that. One has to say this here is a relative point of view. All this, I mean, this renormalization group equation normally one loop, two loop, or I think here perhaps partly three loop. It gets very complicated. So this is a perturbative thing. Maybe, and here we are already at 10 to the 9 GeV, maybe there's something non-perturbative already happens somewhere here. It's also a problem anyway, but since nobody can do this, who knows? We stick with perturbative for the moment. So how unique is the standard model? That's something we did in Marseille a couple of years ago. So just take some internal space and try to classify models that come out with respect to the number of summons and with respect to some physical criteria we just choose for our convenience. As I said, the standard model looks roughly like this, or we can also replace the quaternions here by like 2 by 2, complex 2 by 2 matrix. So there are different ways of constructing it, and different possibilities to do that. And then we just wrote a physicist shopping list. This is just something we like to have. It's nothing, there's no deep reason in the sense that there's mathematical force to choose something like that. So what we want to have is some irreducibility, so in sense as small as possible, internal Hilbert space, allow that the fermion mass spectrum is non-degenerate, so that we can have in principle different fermion masses, because we observe fermions with different masses. Just and another really important bit is that it's free of harmful anomalies. By harmful anomalies, an anomaly is a symmetry of the classical theory, which is not respected by the quantum field theory. And if you have gauge symmetry, so a symmetry coming from a principal fiber bundle, that's something you usually want to be respected by the quantum field theory. If that is not the case, it's usually a bad thing. But one can find it's a matter. It can be seen as a matter of representation of the gauge group, and we don't want these in, so this fixes us some details about the algebra representation. So this is just color groups. One can define what a color group should be, and so this is just the shopping list we put in, just for our convenience, and see which models, which kind of internal spaces work.
So anomalies can be understood without quantization.
They cannot be understood without quantization, but you can write them down without quantizing. So because it's basically trace of the.
So you take something from.
Yeah, we just
standard approach.
Yeah, exactly. And you can write down in just as representation on the space, so it somehow fits in. Another thing would be the.
Know that if you quantize this eventually, this will be the right.
Okay, one can show that this is exactly what happens. So that a certain choice of representation leads to anomalies, and anomalies correspond, or certain anomalies correspond to them. Yeah.
So how do you see them as anomalies here? How do they appear as anomalies? What?
Oh, just the representation. So
It's
they don't appear at all. So we just take something from quantum field theory and just use it. They don't appear. They only appear when you quantize the whole thing.
Yeah, that's what I'm saying.
Yes,
so they're not really anomalies.
At the moment, they are not really anomalies. They become anomalies as soon as you quantize.
Yeah.
Yes. So, and then if you classify, I mean, you can do it either in KO dimension 0 or KO dimension 6. You basically find with 1 or 2 summons in the matrix algebra basically nothing. With 3 summons, the standard model strangely appears as one of the simplest models you can find. And this is quite surprising considering how complicated it is from the differential geometry point of view. With a slight, well, it's a bit more general than the standard model in the sense that you can choose the group which tells you the color group of the quarks can be chosen fairly arbitrarily. So this can be, you can have 2, 3, 4 colors, whatever. We know we have 3, but we cannot say why. But it's the other left-right parallel model comes out right, which is already something. And the other extra model we found basically was what we call an electrostrong model, which is basically something like, looks like a model which has electrodynamics in it and color group, so and a strong force from a physical point of view. And basic idea was now, okay, we have a standard model, we find that, that's great, we find this electrostrong model, And can we use these as building blocks? So these are like basic blocks of finite spectral triple. Can we build bigger spectral triples out of these, which give perhaps interesting modes to understand? So just take a look. A similar approach has been taken by Thijs van den Broek in his PhD fields, where he looked for building blocks which are supersymmetric and try to build out supersymmetric extensions of the standard model. So it's a fairly, I mean, it's just a building block you get, and then you try to play around with it. So that's model building. So how do you get then beyond the standard model? You find a finite geometry that has a standard model in a certain sense as a submodel, so all particle content and so on, which is already quite tricky. Then you make sure that everything is anomaly free. That's even more tricky, so that this thing is fulfilled. Then you compute the spectral action to get constraints on the parameters. This is straightforward. You determine the scalar scale with a suitable subset of these constraints. Already not so straightforward which subset to choose, but usually you have to hint from the standard model. You use these renormalization group equations to write everything down from the cutoff scale and get hopefully information on interesting parameters, and then you check with experiment and start over again because you failed. Okay. This is the usual thing that happens. And so perhaps I start with some failures. So what do we construct? The first thing was what we call the AC model. So you basically enlarge the algebra, you enlarge the Hilbert space a little bit, you add two new particles with opposite charges. Funny thing is, opposite electrical charge, they can bind into little atoms, and if they are heavy enough, then these atoms are formed very early in the universe, are very, very small, very, very hard to detect, and are, strangely enough, good particles or good candidates for dark matter, even today, if they are just heavy enough. So dark matter can be quite a complex thing. It doesn't have to be a single particle, it can also be, you could, in principle, one could imagine a whole dark universe which just doesn't really interact. Dark matter is much more flexible than one thinks usually. We had something called, every model basically we built turned out to be already known in particle physics. Particle physics built almost everything I have even I mean, there are infinitely many models you can build with a differential geometric approach, and I think all of them have been built. So to everything there's a name. So came up with one particle with this new particle with a new color. They were already known as theta models by Okun, I think. Then we built another thing with new vector coupling to the SU2 subgroup of the standard model, and they were already known as vector doublet models. The problem is all of them have Higgs masses greater or equal to 170 GeV, so that's that. And they can, in general, not fulfill these constraints on G1, G2, and G3. So even if you get U1 in it, just doesn't work. This model here may perhaps be saved. I would have some hope that one can save this model by enlarging it a little bit, but I mean it's difficult to play around with it. One model which is excluded, but which was quite interesting, was a model I found a couple of years ago, where I enlarged the internal space quite stupidly just by 2 copies of C. So just simple thing. And took here instead of the quaternions 2 by 2 matrices, which gives you then an x raised 1 in the whole game. And you include new fermions, which are basically symmetrically coupled to the U1, so left and right coupled equally. It's called vector singlet then. And the interesting thing is, from the fluctuations, you get an extra Higgs-like field from this U1 here. And the Lagrangian looks slightly different. This is the Higgs Lagrangian, basically with this gives you this Mexican head thing, what you get out of the spectral action. You get is exactly the same for this new scalar field, which I also call sigma here. but you also get an interaction term between the Higgs field and the new sigma field. I don't want to get into all the details here. The basic point is that this changes the thing you would measure in this model as the Higgs mass or the Higgs coupling is no longer this supporting coupling here, but you have to diagonalize these supporting couplings, and so everything gets slightly altered a little bit because you have here the forward matrix, and what is measured are actually the eigenvalues of this matrix. And what turns out, if you then put everything in, find the cutoff scale, 10 to the 17 GeV again, and find the relations and play around with this, then it turns out that you have another free parameter in the game, which is basically the vector expectation value of this new field here, which you can choose. And it turns out if you just choose it heavy enough, then one mass eigenvalue goes up like this, and the other mass eigenvalue approaches a certain value. This is here 117 GeV line. I put this line in because at the moment this was the exclusion limit where we knew that the Higgs is not there. And funny enough, approaches the second light eigenvalue approaches something about around 120, 130 GeV, and becomes more and more Higgs-like in a way from the behavior, the heavier the other one is. So, and I think I wish to point out that this was a couple of years before the detection of the Higgs. So, but unfortunately, it doesn't work because it doesn't fulfill all the constraints. It's too standard model-like. And then after the Higgs was discovered, I thought, well, everyone can also solve this problem. So what did I do? I'm not very imaginative person, so I added another copy of C's. Works well, doesn't spoil the gauge group too much. You get a couple of extra fermions, so in the end, 1, 2, 3, 4, 5, with the representations, and you get this new scalar field. Important bit is standard model is completely blind to this new U1, and the new particles, apart from these here, these couple to standard model, but the other particles, especially the new scalar, are completely blind to the standard modification. This is important because otherwise you get ugly mixings. You get essentially the same Lagrangian with extra bits, but you have here fermions, extra fermions in the game. They alter the renormalization group equations and help you a bit. And the constraints look like this. I put just, you have some choices there. I just took a very convenient point for me in the whole parameter space because, I mean, what one should do is do a parameter space analysis, see about stability and whatnot. I never did that. I just took a point which I could use to calculate, and funny enough, it seemed to be a good point. So the cutoff scale raised a little bit up to 10 to the 18 GeV, so closer to the Planck scale. I put in top mass and the Higgs mass, so this is now something you have to put in, but this is now, if as soon as you have this field in it, it somehow appears that, I mean, it becomes a little bit less predictive with respect to the Higgs mass, and what you find then is that you can fulfill these constraints and get actually a model which looks like the Higgs at the right mass and some other particles heavier than it. And some of these fermions may also be interesting because they acquire masses less than 50 GeV, but couple very, very little to the standard model and may perhaps be good candidates for dark matter. So, but there are models like these as candidates for dark matter, but whether it works or not, I don't know. One, and also you can fulfill the this constraint for the other couplings because they get altered also a little bit, so you can get this. It was the triangle graph. The data was showing where the lines didn't converge, and so you can make them converge. So this works. One word of caution here: if you have more than one and one subgroup in the game, which are represented on the same one-dimensional Hilbert space, what you get is mixing of the different Yang-Mills terms. So one Yang-Mills curvature can mix with the other Yang-Mills curvature. This normally only appears in quantum correction called kinetic mixing. But if you have, if you are not careful enough with your representation, you can mix the photon with other U1s. if they get massive and so on, then you get set primes, so-called, so other massive particles coupling to the standard model, which somehow spoil the whole thing and are excluded experimentally. So one has to be very careful when adding more than one U1 in the game. And exactly because of these terms and these terms here. Okay, some alternatives which have been there: rank symmetry, half-Salam type, non-associative spectral triples. So other ways beyond the standard model, how do you write your color operators, and so on. And to conclude, before I have just concluded with some questions. Are there viable star-type candidates in the game? What about the rest of the parameter space? I just picked one convenient point. Going high to higher than one loop in the renormalization group equation, I think this will play a role. Is it a subgeometry where I construct the one-of-one Chomsky type geometries which lead to these Party-Salam models? I have no idea. And classified verbs, but most salient points is what about Lorentzian spectral triples and something like the Lorentzian spectral action. This is somehow at the moment ongoing work here. Kuhn and Hegel. So we are currently looking at the last line because we think this is too difficult for us. Thank you very much.
Okay, no much time for questions, but well, your signal to equality seems to be quite wide, right?
Yeah.
So is there any hope that you will found on the next round of LHC or will exclude?
Yeah, I guess so. At the moment, definitely, or I talked to Hausdorff phenomenologists, and they said at the moment, the Higgs is 93 to 94% Higgs-like, confirmed to be, so there's probably enough. Is enough space, but as I said, perhaps there's different points in the parameter space with heavier sigma fields, and so there may be routes of escape. But this, I would guess so, because they should, next round should be close enough to 100% Higgs in a way, and then one sees that can't be mixing of this sort, at least not with the relatively large sigma field. But so yes. Should be excluded. Whether, yeah.
Or found. Or just found, yeah.
Or found, I mean, yes, of course, but as I said, most important thing.
Yes.
And.
No, but this line goes up. I mean, you can take it as high as you want, can't you?
Yes, but then at the moment, you go, this is the 126 line, you go slightly above. But of course, I mean, I'm still running now here over 10 to the, over 40 orders of magnitude. Even, I would say it would even be good if you're off, I don't know, 5 GeV or something like that. It's a bit too, you ask a bit, one probably ask a bit too much if you run over 14 orders of magnitude and you're on the spot within a few 1% or so it's probably not realistic anyway. So the basic direction seems to be not too bad.
Okay. No other questions?